All right, going from our discussion of standing waves and traveling waves, now nodes and antinodes came up, and let's do a little more discussion on what they are. So what are nodes and antinodes? So when we see a standing wave pattern, like the one we see to the right here, okay, and it's moving for us, what we see is we see places where the interference straight up and down, right? I mean, that's where that object, you look along that line where the wave is right here. Not a whole lot of different movement. Again, nodes are where we don't see a whole lot of movement or zero energy. Here, where the crests and troughs are at their greatest distance, this is what we call the antinode. Okay, the maximum displacement is the antinodes. Minimal displacement or no displacement is a node. So, typical standing wave diagram would look like such. The nodes are produced where destructive interference occurs. So here, 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 and here. And the antinodes are where completely constructive interference occurs. Here, 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 and here. Okay, so nodes and antinodes. Do not confuse them with crests and troughs. All right. The point of the largest maximum displacement is a crest, and large negative displacement is a trough. Now, these represent points in the disturbance that travel from one location to another. Okay. The antinode, on the other hand, is a single point on the medium. A single point in the medium that is stained in the same location. A single point, not the movement of this change in amplitude, what we see with crest and troughs. Now, antinodes vibrate back and forth between a large upward and a large downward displacement. So when we look at a wave here, right, when we talk about amplitude, we just talk about it to the equilibrium and back up, or equilibrium and back down. That's our amplitude. But our antinode vibrations are actually both sets of crest and trough. So they're not actually part of a wave. It's something that we see. Okay? It's the pattern of interference that we see. So standing wave is not a wave, but a pattern of interference. The nodes and antinodes are just points in the medium that make up the wave pattern, points that we see on the wave. So let's take a look here. How many nodes do we have here? Again, nodes are here, right? 1, 2, 3, 4, 5, 6, 7, 8 nodes, right? And then the number of antinodes, 1, 2, 3, 4, 5, 6, 7. And we can count those just by looking at the standing wave pattern. The number of nodes for the entire pattern, again, 1, 2, 3, 4, 5, 6, 7, 8, 9. And destructive interference occurs at what points? Well, at D, at B, and at C. That's where we see destructive interference, B, D, and C. And so we can look at standing waves and patterns, and we can identify things we got to identify. Now, harmonics and patterns, and what harmonics are in the whole scheme of things. So here's a standing wave pattern, and this is just a single antinode and 2 nodes. Okay. Now, this is called the first harmonic. The first harmonic happens when we have just a single antinode, okay, and 2 nodes between it. That's called the first harmonic. Now, when we have a nodes at 2 ends and a node in the middle, okay, that's called the second harmonic because we have 2 antinodes. And hopefully you can start to see the pattern here. When we have 2 with 2 nodes in the middle, but more importantly, we have 3 antinodes, that's going to be our third harmonic. So how we can associate this and what the pattern looks like. First harmonic has 2 nodes and 1 antinode. Second harmonic, 3 and 2. Third harmonic, 4 and 3, and so forth. And you can see how it works. And then here's the mathematical pattern to it. To the nth harmonic is n plus 1 for nodes, and the n for the number of antinodes. And our diagrams are to go along with it. So that's how we can determine harmonics and nodes and antinodes.